Hello everyone, my name is Bingyin Zhao. I am a PhD student at Clemson University. My advisor is Dr. Yingjie Lao. Today I will be talking about our WACV 2022 paper towards class-oriented poisoning attacks against neural networks. With the development of machine learning, neural networks have achieved remarkable success in many fields. However, modern DNNs require large amounts of training data to achieve good performance, which provides an opportunity for data poisoning attacks. The data poisoning attack is a training-based attack, where the attacker can inject a fraction of poisoned data into the training dataset and affect the training process. The attacker can introduce malicious behavior to models trained on the poisoned dataset. Poisoning attacks can be broadly classified into two categories: availability attacks that aim at degrading overall model accuracy, and integrity attacks that seek to cause misclassification on specific instance. In this work, we advance the adversarial goal of availability attacks to a class basis. Rather than only focusing on degrading the overall model accuracy, we also want to manipulate the behavior of each class. We propose two class-oriented attacks: the class-oriented arrow-generic attack and the class-oriented arrow-specific attack. For the COEG attack, we not only want to degrade overall model accuracy, but also want to classify all the images into a supplanter class. For example, we want to classify all the images in CIFAR10 to an automobile class. For the class-oriented arrow-specific attack, we only want to degrade the accuracy of a specific class, which we call the victim class. At the same time, we want to remain the accuracy of all other non-victim classes. For example, we set the host class as the victim class, and we want to degrade the accuracy of this class by misclassifying the images into other classes. Meanwhile, we want to keep a high test accuracy on all the other classes. To achieve the adversarial goals, we propose class-oriented algorithm to generate poison data. For the COEG attack, let's take the CIFAR10 dataset as an example. We first pick an arbitrary seed image from any class other than the supplanter class. To generate effective poison samples, we want to retain the feature information associated with the ground truth class and reduce the feature information of other classes by enlarging or dwindling the corresponding larger outputs. Here, we want to decrease the larger value of all other classes and increase the larger value of the ground truth, which is the ship class. Then we backpropagate the gradients to update the image. We iterate this process for several rounds and assign the label of the supplanter class to the poisoned image. However, it is very computationally expensive to optimize the largest value of all classes. Thus, we propose a lightweight solution based on two facts. First, the classification is determined by the largest probability. Second, only the supplanter class is the target. Therefore, we only focus on the supplanter class and the ground truth class. Here, the automobile is the supplanter class. We want to decrease the large value of the automobile class and increase the value of the ship class, and then backpropagate the gradients to update the image for several rounds. For the COES attack, we need to take care of images from both the victim class and the non-victim classes, since we only want to compromise the accuracy of the victim class. For images from the victim class, we perform the same operation as in the COEG attack. For images from non-victim classes, we only focus on the ground truth class to retain the feature information. We evaluate the COEG attack with two metrics: the overall test error that indicates the accuracy drop, and the change to target rate that indicates the fraction of images classified as the supplanter class. Our proposed method achieves high test error and the CTT rate in both single-instance attack and attack with a set of poison data. For example, we set the airplane as the supplanter class. Our attack makes the neural network classify most images to the supplanter class. For the COES attack, we use change from target rate to measure the accuracy drop of the victim class. For both experiments, our attack achieved high CFT rate on the victim class and maintained high accuracy on the non-victim classes. Please check our paper for more details. Thanks.